G'day YouTube and welcome back to the ASX Portfolio channel. My name's Jonathan. If you haven't been here before, here we like to do financial mathematics and how to actually implement algorithms in Python. So if you want to see more of that content, I'd really appreciate a like on this video and then subscribing to the channel. So without further ado, let's get into this video. Today we're going to be talking about how to actually choose the parameters for the binomial tree pricing model. Now, what does this mean? We need to choose an up factor and a down factor. We also need to choose the risk neutral probability. So there's a couple of methods that we're going to be going through today in this video and then implementing in Python for a call option, a European call option. So the two that we're going to talk about first is the Cox, Rose and Rubinstein, the CRR methodology. Now this is where we choose equal size jumps for our underlying distribution. Now, the other method we're going to use is the Jarrow and Rudd, the JR method, where we choose risk-neutral pricing probabilities to be equal to a half. So these methods are very good when you only have small time frames and a small number of steps, so they're good for approximations. So unfortunately, a limitation of both of those methods is that they only work for short-term approximations. And the reason that is because we're not really getting the best approximation of these underlying distributions that we could be. Now, one of the ways that we can get around this is using the underlying as the geometric Brownian motion and approximating that, because the natural logarithm of the GBM actually has a constant mean and variance, so it's normally distributed. So what we do is we're actually going to turn this tree into the natural logarithm of asset prices. So by matching the means and variances of this new natural logarithm tree, we're going to be able to come up with two new formulations. Now this is the equal probabilities, or EQP methodology. And then we're also going to be able to come up with equal jump sizes, and this is actually called Trigeorgis method. So let's just jump into the maths. So just taking a step back, we know that there's the binomial tree parameters as we have here. We've got the up factor and the down factor. Now I wanted to put this in perspective of our probability space, our filtration and our outcome space. We won't worry about filtration for a second, but here we have two outcomes. We've got like a coin being tossed, heads and tails. Now they have physical probabilities that we can see here, P and 1 minus P. So we have the two outcomes, heads and tails. We start off with an asset price of S0. If we get heads, then it's the up factor minus S0. If we get tails, then we have the down factor times by SO. Now it's really important to understand that the sum of the probabilities of all these outcomes, the physical probabilities, has to be equal to 1. So which are the parameters that we need to actually classify? Well, it's the up factor, the down factor. However, it is not this probability that we can see here. This is the physical probability, and as we found out in the first pricing video about the binomial option pricing formula, we actually need to choose the risk neutral pricing probability. So for the risk neutral probability, we're actually going to be representing that here by P tilde. Now the tilde is just representing the special probability that it is actually under the risk neutral probability measure. So that is our probability space, let's call it Q. So now that we've got that clarified, let's jump into the different formulations. For the JR method, essentially we have a free variable which we need to choose. So we're trying to match the mean and the variance. So we've got two equations and three unknowns essentially. For the JR method, we choose P to be a half. And then as a result of that, we end up with these U and D factors. Now, in contrast, for the CRR method, we actually choose the up and down factors to have the same size but opposite. So by choosing that, we then end up with a probability factor as you have here on the screen. So now for our new tree in terms of the logarithm of our underlying S, now we have X with an up probability and a down probability, and with two outcomes where X plus the change in X up and X minus the change in X down. Now this is over a time period. So using the same methodology where we're going to match the means and the variances, we're going to consider what is the expectation of a small change of X. So we're going to consider the expectation of a change of x, and then we're going to consider the expectation of a change of x squared. Now, by doing this, we can match the means and variances and end up with these two formulas that you see on the screen. From there, we have a choice to make. We can either choose to say something about the probabilities, the risk-neutral probabilities, P up and P down, or we can choose to talk about and define the actual jump sizes. So these two theories have defined either one of those. So for Trigeorgis, they've talked about equaling the actual jump sizes, and then therefore the resulting probability is as you have here on the screen. And then for the actual equal probabilities, EQP, they have made the risk-neutral pricing probabilities equal to 1/2, and then you result in the factors that you have here on the screen. So now we've taken a look at these 4 different methods to actually choose the parameters for this binomial option pricing model. Let's jump into Python, implement them all, and compare them for a European call option. So let's now jump into the Python implementation for choosing these parameters. So as we've said, we're going to be using or pricing a European call option, and we're going to use the CR, JR, and the EQP and TRG methods for choosing those coefficients, the up and down factors and the probability. So we're going to need the NumPy module, so import that. We're going to be using the binomial tree representation as we've been going through. The initial parameters are on my website, but we're going to be using initial stock price of 100, strike price 110, time to maturity half a year, 6% risk-free rate. We're going to be using 100 time steps, and then a volatility of 30%. And again, we're going to be valuing a call. So straight into the Cox, Rose, and Rubinstein method. So here we're looking at equal jump sizes. So I've copied the binomial tree slow function that I've used in a number of my videos. So feel free to go to my website, download it, and start with this as a base. So the first thing you'll notice is that we've still got up and down factors here. So this has to be changed to sigma. We can leave Q as it is, but we're going to be now calculating the up and down factors here. So the up factor, as we have on the screen, the formula on the screen that you should see right now, we can just start plugging away. So this is going to be NumPy exponential. We're going to use sigma multiplied by the square root of dt there. So, and all we need to do for D is it's a recombining tree, so it's 1 over U. Q is going to be calculated using this formula here, because of course this formula for risk neutral pricing applies for all binomial option pricing trees, so that is fine to leave as is. Now, are there any other alterations that we need to make to this code? Yes, let's change the title. Let's call this CRR method. And we'll copy and paste that down here, placing in the correct parameters, sigma, and we get a value of 5.77. Great, so now let's copy and paste this and change it for the JR method, so the Jarrow Rudd method. So the JR method, we're doing a similar thing here, except we're going to have equal risk neutral probabilities. So this Q is going to be 0.5. So once you've established that, then we just need to change the up factor and down factor. Let's start with the up factor. We're going to introduce something called new here, and this is just going to be R minus 1/2 of the volatility squared. So this is our value new, and we'll be using that going forward. And we're just going to now use new times dt plus sigma times by the square root of dt. Excellent. And for the down factor, we can do something very similar. So we'll just copy and paste that there, but it'll be minus sigma times the square root of dt. So that's the only changes that we need for the formulation for the JR method. Let's make sure that we're calling the right function, JR method. And you can see there we get a very similar call price with those strikes and terms and parameters there. So let's move on to the equal probability method. So we'll copy paste that. Now here, if you remember, we're actually using the natural logarithm tree to price. So here we're going to equate those risk neutral probabilities. So it's a little bit different in terms of how we calculate these parameters. So nu is going to stay the same. That's that funny looking V on the formula on the screen. And essentially we need to now calculate not U and D, but dx up and dx down. So we're also going to have PU for the probability up and PU for the probability down, and we can get rid of Q. So for dxu, we're going to have 0.5 times nu times by dt. Now then we're going to have a half times by numpy square root, and that'll be 4 times sigma, if we spell sigma correctly, to the power of 2 times by dt. Now once you've done that, we'll subtract 3 times nu to the power of 2 times by dt to the power of 2. And we probably could have just multiplied nu and dt and taken them both to the power of 2, but anyway, that'll work and that'll be fine. So we can copy this formula because it's pretty similar for the down factor, except here it's 1.5, so 3 over 2, and we're subtracting this value here. So just make sure that that's okay. It's a half the square root of 4 sigma squared times dt minus 3 nu squared times dt squared. So that's all fine there. Now the probabilities, of course, are equal to each other, so they're just a half, but we'll calculate it with PU, and PD is 1 minus PU. So now the initialization of the stock prices slightly changes. So because we have a different methodology of the tree, we're not using the down and up factors anymore. So we need to multiply this by the exponential of those factors. So it's an n time steps times by the amount of down steps we have, so that's dxt. So this will give us the very bottom of that final, the worst case of the price at the end of the time period, and all we need to do now is take a multiplying factor, which is going to be np.exponential, the difference between dxu and dxd, and essentially what that's doing is just going up one step back in the tree and then up. So we're just calculating that last column of asset prices that we require for this binomial tree method. So that should work fine there. Once you've done that, the final payoff is just the exact same, but stepping backwards through the tree. So our backward recursion is just going to be, instead of Q now, that probability, we're going to be using P up and P down for our risk neutral probabilities. So once we've got that, we'll call it the appropriate function, EQP, and we can make sure it runs. And again, we get a similar value, 5.74. So we'll copy and paste that, and we'll do the TRG method now. So this is probably the most accurate of the three and is a very good method. And robust, so over large periods of time, if you're valuing over many years with many time steps, this is probably your most accurate function. But you'll see that in a second when we compare the three of them. So again, we're going to have a call option, so our DXUs and our DXDs, so we have the same thing, except we can get rid of that term, and we've got the square root, and we're just going to have in there, looking at the formula on the screen, we've got sigma squared times dt plus nu squared times dt squared. And the down factor is just going to be the exact same but negative. So we can just go negative dxu. Now the probabilities are a little bit different. The probability up is 0.5 plus 0.5 times by nu times by dt divided by dxu. So once you've got that, we can calculate the probability of down, 1 minus pu. So that is exactly the same. All these things are exactly the same, p up and p down. So you can just press run once you've satisfied that you've typed it all in correctly, and you get 5.77. So now that we've implemented all 4 of those in Python, we're going to compare them. Now I'm going to be using the black-scholes formula from this pyvol-lib library. Just feel free to watch if you want to get onto this, download it from our website. So I'm going to import those dependencies. I'm going to look at the time steps from 10 to 500 time steps, taking a step 10 each time, and we're going to calculate all these different call prices with the 4 different methods. We're also going to compare it to that black-scholes option price using pyvol-lib library. So once you run that, you can see here this graph over time of option prices and the convergence as you increase n, and our 3 different methods. What's interesting is that the TRG and the CRR method are actually spot on top of each other for these call options here with this given time range. What is really interesting is looking at these convergence for different option pricing, and one that I would recommend, that I probably won't do in another video because it'll be very similar to this, but looking at the American put option and this convergence over time, I think you're going to get drastically different results using these 4 different methods to calculate those factors. So hopefully you got a lot of value out of this. If you did enjoy, please, I'd appreciate if you liked the video, and if you want to see more content like this, feel free to subscribe to the channel, and we're going to be uploading hopefully every 3 days now, so stay tuned. Until next time, YouTube, see you later.